Hey chemistry students, this is Miss Ruark. This is Vodcast 7.4 where we're going to talk about an ideal gas and the ideal gas laws. Okay, so far we've been talking about, well, not ideal gases. We're talking more about real gases. And so in this one we're going to be talking about what we call an ideal gas, which is describing the condition that the gas would behave if it was behaving ideally and at the certain pressures and temperatures. Okay, so the ideal gas law is going to incorporate all four variables. It'll incorporate pressure. It'll either be in kilopascals or atmospheres. It can be in torricellis, but you want to make sure that you change it into kilopascals or atmospheres. Your volume will be in liters. Number of moles will be moles, of course. Your temperature in Kelvin. Excuse me. And then you have this thing called R, which is the ideal gas constant. Okay, and the ideal gas constant is it's a constant. It remains constant at all times. It does not change. And the number will be different depending on the units that you use for your pressure. Okay, and I believe I'll talk about that in just a little bit. So the ideal gas law is going to be used to describe the condition of the gases as they are right now. If you're trying to figure out which one to use, the ideal gas law or the combined gas law, okay, if we're talking about how the gas behaves right now, you would use the ideal gas law. If you want to try to predict what it will be or what your conditions will become when you change other conditions, that's when you would use your combined gas law. Okay, so ideal gas law, you would use it if there's only one set of conditions. Okay, one set of conditions is for the ideal gas law. If you have two sets of conditions, then you would use your combined gas law. Okay, that's for the combined. And that was from the last podcast. All right, so let's do an example. Okay, actually, let me go back to here. Let's go back one more time. Okay, here, let's talk about that R value. All right, that R value can have two different numbers to it. One of them can be 8.341, and that's if you have kilopascals as your unit of pressure. Okay, so it would be kilopascals times liters over moles times Kelvin would be your units. Now, you could also have it in atmospheres, and if it was in atmospheres, it would be 0.0821. At least I think that's the number, and that would be ATM times L over moles times Kelvin. Okay, so you'll have one of those two that you would use at all times. Now, I like atmospheres, so I'll probably end up using the 0.0821 all the time, but that's just a personal preference on my part. If it doesn't specify, you can use either one. Okay, so example here says how many kilograms of methane, CH4, are in a 225 liter container at 150 kilopascals and 35 degrees Celsius. Okay, so we're looking for kilograms, so we want to know how many kilograms of CH4. Okay, and we know that the volume of this container is 225 liters. We know that the pressure of this gas is at 150 kilopascals. And we know that the temperature is at 35 degrees Celsius. Okay, so we know all of these things. We know that we only have one set of conditions. And how do I know I only have one set of conditions? Because I only have one thing for V, one thing for P, and one thing for T. I don't have another set. I don't have an initial and a final. So for that, we would have to use the ideal gas law. Now, you'll hear me refer to this as PIVNERT. Because if you look at it, it looks like PIVNERT, right? PIVNERT. Okay, so instead of saying ideal gas law, I'll probably say PIVNERT. All right, it's the same thing. Okay, so we're going to use this right here, and we've got to plug in and solve. Well, we've got our P, we've got our V. We don't have N. What does N stand for? Remember, N stands for moles. If I get the number of moles, can I then use that to find grams? I sure can. Okay, so we're probably going to solve for N. What about R? R is that gas constant. Remember, R is going to be one of those two numbers that I showed you. Well, we've got kilopascals here, so we'll use that 8.3, what did I say, 8.341, 8.31, I think it's 8.314, sorry. I'm going off the top of my head on this one. All right, so that's going to be kilopascals times liters over moles times Kelvin. All right. All right, yeah, it's 8.314. Sorry about that, guys. Okay, so all we have to do is plug all this in, and then we solve for the variable that we don't have. So our P is 150 kilopascals. Our V is 225 liters. N we're looking for. R is going to be 8.314. And then we have kPa times liters over moles times Kelvin. Now you want to get used to writing your units so you know what cancels, and that way you know what you're left with in your answer, right? I know you guys don't like writing units. Write them. Okay, and then our temperature in Celsius, but we can't do Celsius. We need to change that to Kelvin. So we have to add 273 to that. And when we add 273 to that, that becomes 308 Kelvin. Okay, now we can plug that in, 308 Kelvin. Okay, so now to get N by itself, we need to divide both sides by 8.314. Okay, times, alright, and 308 Kelvin. Alright, this cancels here. And then on this side, 8.314 kPa times liters over moles times Kelvin. And then that gives me 308 Kelvin here. Alright, what units cancel before we do anything else? Kelvins cancel, kilopascals cancel, liters cancel. We're left with moles in our answer. Okay, so now all we have to do is the math to figure out our answer. Okay, when we do the math, the calculator gives us for N 13.1799 blah 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 blah. Alright, but that's moles of methane. We don't want moles of methane, we want grams. So we've got to go from moles to grams, and you guys know how to do that, right? We put 1 mole of methane here, and we put grams of methane up here, and that would be 12.0. I'm just going to do it over here. 12.01 plus 4.04 gives us 16.05. All right, so 16.05 there, and we multiply that times our number of moles, and we end up with 211.53784 ... grams of methane. Oh, but that says grams, and that says kilograms. So we got to change this from kilograms, or from grams to kilograms. Remember, we move our decimal over 3 times, so this would be equal to 0.2115374 kilograms of methane. Okay, but we're still not done yet, right? We need to look at significant figures. Here we have 3, here we have 2. Temperature doesn't count, so we need 2. So 0.21 grams of, kilograms of methane. And that's how you do it. Okay, I know it's a lot of work. Okay, let's do another one. Find the number of grams of carbon dioxide that exert a pressure of 785 torr at a volume of 332.5 liters and a temperature here. Okay, so we're looking for grams again, which means that we've got to find moles. Okay, we've got a pressure of 785 torr. We've got a volume that's equal to 32.5 liters. And we've got a temperature that's equal to 32 degrees Celsius. Okay, to solve for Pivnert, okay, your R value is only going to be in ATM or in kPa, so you need to convert this. Convert it to either ATM or kPa, whichever one it is, that's fine. And then use that corresponding R value in for R. Make sure that you change this into Kelvin as well. This can stay in liters. Okay, now I'm going to let you solve this because, well, I've just shown you all the hard stuff. Now you just got to do is plug it in and solve. Remember, when you solve for N, though, N is moles, and you got to go from moles to grams for your final answer. Okay, make sure you do that. I'm checking for this when you come to class. All right, for number 3, if the density of a gas is, oh, that's not fair. I'm not doing any of those with you, so we don't have to do this one. Yay, let's keep moving. Woohoo. Okay, so what's the difference between an ideal gas and a real gas? Okay, so an ideal gas is one that follows all the gas laws at all the temperatures and all the pressures. It's going to conform precisely to all assumptions of the kinetic molecular theory. We're going to assume that the particles have no volume and there's no forces of attraction between them. We're going to assume that this is the perfect gas and it behaves perfectly all the time. And guess what? There's no such thing as an ideal gas. They don't exist. All right. So in comparison, we have actual real gases, and real gases do have volume. real gases do have attraction. IMF stands for intermolecular forces. That's forces of attraction between those particles that pull them close together. They do differ, mostly at low temperatures and high pressures. And the real gases is the true picture of what a gas really looks like. Okay, so if somebody asks you, what's the difference between an ideal gas and a real gas? Well, an ideal gas is something that would be perfect in a perfect world. We don't have those things. Okay, and a real gas is what we really deal with on a daily basis. Okay, so why do we use the ideal gas law to help to determine the conditions for a gas? Because it's one where we can say, assuming that this gas is going to behave like this, we can choose what its different conditions are. And it actually does. Most gases do follow the ideal gas law at extremely low temperatures and extremely high pressures. So it's really not that bad. We can use it. And yes, if we were to get more into it, we could actually say, hey, guess what? We'll only use it for these conditions. But we're not going to. We're going to say we use it all the time. Make it easy for you, right? Okay. Well, what if I have a mixture of a gas? Okay, not all my gases are going to be pure. So what if I have a mixture of my gases? Well, if you have a mixture of gases, we have this thing called partial pressure. And it just says that the pressure exerted by an individual gas in a mixture of gases, you add all those together and you get your total pressure. All right, so John Dalton, the father of the atomic theory, is the one who came up with this law of partial pressures. And he says for a mixture, the total pressure, okay, so the total pressure would be equal to the partial pressure of the gases. So that means that the total pressure is equal to the sum of the pressure of all the gases that are involved. Okay, I think, yes, I do. Good. I have an example. All right, so let's put that into practice. So it says here we have a 250 milliliter sample of oxygen, and it's collected over water at 25 degrees Celsius, and here's your pressure. What is the pressure of the dry gas alone? All right, so what happens here is your container with your water. Okay, we've got here's our flask or our whatever we're going to collect it, and we're collecting this water inside, or we're collecting this gas inside of here. Here's your gas that's collecting here, your gas or your oxygen. It should be oxygen, right? And as this oxygen is being collected here, here's your water level. It's going to push that water level down. So your gas is going to collect here. Okay, your water level is going to keep going down here. Well, just above the top of the water in here, there is vapor. Okay, and it's water vapor. And water vapor has a pressure. And the pressure of the water vapor at 25 degrees Celsius is 23.8 millimeters mercury. Okay, well, the total pressure of this system, the total pressure of this system, it says here, is 760 millimeters mercury. And we know that the pressure of the water vapor is 23.8 millimeters mercury. We don't know what the pressure of the oxygen is. That's what we want to know. But we know that we have total pressure, we have oxygen, and we have water. And that's all we have in here. So if we were to use that, PT, total pressure, is equal to the pressure of the first gas plus the pressure of the second gas. All we have to do is plug in for those, right? So we plug it in. We've got 760 minus 23.8 millimeters mercury. And why did I minus it? Because here we've got to subtract, right? I just went on ahead and stuck it all together. And that would give me the total pressure. Okay, well, if I take, or not the total pressure, sorry, the pressure of the oxygen. All right, so I take in my calculator and I put 760 minus 23.8. And that gives me 736.2 millimeters mercury. Okay, significant figure rules for addition and subtraction. There's one decimal place or one number after the decimal, so we need one number after the decimal here. Okay, and that's all you got to do for partial pressures. And well, yes, some of them will be a little more complicated than that, but that's okay. We'll practice them in class and you'll get the hang of it before we actually have to test. Okay, Oh, movement of gases. So you get two types. You've got a fusion, which is when it escapes out of a tiny hole, and diffusion when it spreads out in space, which is why you can smell cookies when they're cooking in the oven. All right, and that's it, guys. I'll see you.